Good evening, kids. Here I am again with the number system for class 9th and as well as class 10th also. This is very important because the whole concept of mathematics lies on this number system only. From the earlier times, counting was not known to people. They were just drawing shapes and drawing lines on the walls for counting. As the number system evolved, they started writing numbers, and you know the importance of number system in counting and in calculating. So again I am with that concept only, but this time I'm concentrating corely on the syllabus part, and the syllabus part is class 9th exercise 1.1 and the chapter is number system. This is very important chapter because unless you understand the importance of number or number system, you cannot go ahead in mathematics. You cannot go ahead longer in mathematics because for learning mathematics, you have to have a good concept, good grip over this number system. So, as I told you, there are two types of number: real numbers, which are in our syllabus, and I'm discussing only that, has been divided into two parts. In previous lecture, I have discussed it. It is rational numbers. I have told you rational numbers are those which can be expressed in the form of p by q, where p and q both belongs to integer and q should not be equal to 0. And another is irrational number. I have already given you some details about this in my previous lecture. A rational number is written in the form of p upon q, written in the form of p upon q, where p and q both belongs to integer and q should not be equal to 0, otherwise it will go undefined. Something by 0 becomes undefined. This is the definition and this is the form of rational numbers. So any number written in the form of p upon q, where p and q both belongs to integer and q is not equal to 0, is called a rational number. For example, if I write 2 upon 3, it is a rational number. If I say 5 upon 6, it is again a rational number. If I say 7 upon 8, this is again a rational number. If I say 3 upon 0, it is not a rational number. If I say 3 upon 10, it is a rational number. If I say 3 upon 0, it is not a rational number because denominator cannot be 0 because it becomes undefined. If I say 3, if I say 4, if I say 5, they are also rational numbers. So all integers are rational numbers. All integers are rational numbers. So you can say -8, -9, -10, etc. All those are rational number. Now people say me, here is not q written here. So you can say 3 upon 1, 4 upon 1. Better you can write this 5 upon 1. Every time you are getting -8 means -8 upon 1, -9 means -9 upon 1, and -10 means -10 upon 1. So what do you observe? That if there is no denominator, you can insert denominator as 1 here, and that will be the same. So 3 is 3 upon 1, 4 is 4 upon 1, 5 is 5 upon 1. So every time it can be expressed in the form of p by q, and if it is expressed in the form of p by q, where p and q both belonging to integers and q is not equal to 0, those are all the examples of rational numbers. So these are the examples of rational numbers. I think this is clear. But I said you 3 upon 0 is not a rational number because denominator cannot be 0. Q cannot be 0. So this is all about rational numbers. And another set of number is irrational number. Irrational numbers are non-terminating. And what are non-terminating? When you divide a number with another number, the remainder should be 0. That is called non-terminating. Terminating. But this is non-terminating and non-repeating. Neither it will terminate nor it will repeat. So non-terminating, non-repeating decimals are called irrational numbers. In other way, you can say which are not rational, those are irrational. So non-terminating, non-repeating decimals are called irrational numbers. I will see that the examples of this are pi, which was discovered by some mathematician in earlier times. Pi. Actually, pi is 22 by 7. So when it is 22 by 7, then it goes in the definition of a rational number, because both 22 and 7 belongs to integer and 7 is not equal to 0. Therefore, this goes in the definition of rational number. But if it is only pi written somewhere, we take the approximate value of pi. This is not exact value. So people are coming with different values of pi and they never AND. So non-terminating, non-repeating decimal. And therefore pi has non-terminating, non-repeating decimal representation. And therefore pi is considered to be the first irrational number. But when it is 22 by 7, and then it is going in the definition of rational number, then it is not irrational. But if you write only pi here, that is going to be irrational number. So this is irrational when pi is written in the form of pi only, and when it is written in 22 by 7, then it is rational number. Or irrational is pi, because mathematicians have come with larger values, larger decimal representation of pi, and they do not find it terminating or repeating, and therefore this is non-terminating, non-repeating decimal. Also some surds which are represented in decimal but never repeats, never terminates, are called irrational numbers. So for that surds I'll be discussing in the next class, but at first I am taking care of these rational numbers and representation of rational numbers on the number line, and how to find more than 4 rational numbers between two given numbers. So that I'll discuss here. So the first thing is that to concentrate on rational numbers first. So I'm concentrating on rational numbers first. So I'm giving the heading here. This is rational numbers. As I told you, numbers which can be written in the form of p upon q, where p belongs to integer. This is the sign of belongs to. Q belongs to integer, and q never should be equal to 0. So these are the conditions. So any number which is written in the form of p upon q, where p and q belonging to integer and q is not equal to 0, are rational numbers. Now, how to find some rational numbers between two given numbers? For example, if this is the number line, on this number line, this is 0, this is 1, this is 2, this is 3, this is -1, all those are rational numbers, because these integers are also rational numbers. Can be written in the form of -3 can be written as -3 by 1, -2 can be written as -2 by 1, this is -1 by 1, this is 0 by 1, this is 1 by 1, this is 2 by 1, this is 3 by 1. But if someone asks you that find 6 numbers between 1 and 2, and they ask you to find 6 rational numbers between 1 and 2. 6 rational numbers, not whole numbers. Whole numbers are not existing here. Whole numbers are itself 1 and 2, so the boundary is fixed. But you have to find between those two numbers, 1 and 2, find 4 rational numbers. Find 4 rational numbers between 1 and 2. And how to do it, I'm telling you. 4 rational numbers between 1 and 2. Finding 4 rational numbers between any two integers. Finding 4 rational numbers between 1 and 2. So take 1 here, 2 here. Between 1 and 2, I'm not finding too much of a space because 1 is a whole number, 2 is also a whole number. But between 1 and 2, visibly, it does not look that there are some numbers. But if I calculate it, then I can find several numbers. For example, if they are asking you to find only 4 or 5 numbers, you can find it by simply changing it into an equivalent fraction, that is 1 by 10 means 10 by 10. That is 1. 10 by 10 is 1, and here 20 by 10 is 2. Why 10 here? Because I'm multiplying 10, dividing 10, so there's no difference at all. 1 is here. Here also I'm multiplying by 10, dividing by 10, so no difference at all. It is 2 only. So 20 by 10 is 2 only, and 10 by 10 is 1 only. So in between those two, I'm finding some space here. Between 10 and 10 by 10 and 20 by 10, I can find some numbers. So I have got the hope of finding some numbers between these two. That is 11 by 10, starting from 11 by 10, 12 by 10, and goes up to 19 by 10. So how many numbers are there? You can find 4 numbers very easily. That is 11 by 10, 12 by 10, 13 by 10, 14 by 10, and if they ask you to find more numbers, you can go further. 15 by 10, 16 by 10, 17 by 10, 18 by 10, and 19 upon 10. But what happens if 20 reaches here? I'm finding 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers are easily tracked here between 10 and 20. But if they ask you to find more numbers, how to proceed further? You can have another look on this number. This is 1, this is 2. So what do you do? If you have to find 99 numbers, in this way you could find only 9 numbers. And if they ask you to find 99 numbers, how can you do? Multiply it by 100 this time, divide it by 100. Again do the same with this, multiply it by 100, divide by 100. In this way, I am not disturbing the identity of 1 and 2. This is 100 by 100, that is 1 only. This is 200 by 100, that is 2 only. So how much enlargement you are doing in the numerator, the same thing you are doing in the denominator. So multiplying and dividing by the same number does not affect the number itself. So this is 100 by 100 now, and this one is going to be 200 by 100. So if this is 100 by 100, 200 by 100, you can find easily lot of numbers: 101 by 100, 102 by 100. And starting from here, you can go up to 199 by 100, which lies between 100, 1 and 2, which lies between 1 and 2. 1 and 2. So how many numbers? I can find 99 numbers. Similarly, if you multiply it by 1000 by 1000, here 1000 by 1000, you can find 999 numbers. So you can find that things are looking very small, the space is very little, but how a lot of numbers are accommodated in between these two, that is due to the fact that between this spacing there are a lot of points, and every point is representing a rational number. So if you are going from 1 to 2, one small dot is representing a number. One small dot between the dots, and even smaller dots are representing a rational number. So between two given numbers, you can always have infinite number of rational numbers. Infinite number of rational numbers can be calculated between two given Integers, infinite number of rational numbers lie between two given numbers. I'm not saying you natural number or integers, even in fractions also, even between two rational numbers, I can find infinite number of rational numbers, and that I'm going to discuss later on. So better you might have understood how to find numbers between two given numbers. Visibly it does not look that there may be some number, but between 1 and 2 I can have infinite number of rational numbers, and similarly between 2 and 3 infinite numbers lies. And because I'm saying you that a line is a line is made up of very small dots, and every dots is representing a number. So if it is representing a number, so therefore between two given numbers there can be infinite number of points, because a point is what? A line is what? It is just a congregation of points. So if it is having 3 and 4, still you can find alarming number of numbers between these two, which unimaginable but can be calculated, and what I've done here. So the better thing is to do, if you have to find limited number of numbers between two given numbers, you multiply by 10 to both, change it into equivalent fractions. Both of the fractions are to be changed into equivalent fractions, either multiplying by 10 by 10, or multiplying by 100 and 100, or multiplying by 1000 and 1000. And this is the way you can find a lot of numbers between two given whole numbers. But if I try to find numbers between two given rational numbers, how the matter takes. Just see. They're asking you question number 3 of exercise. They say find 5 rational numbers. This time they say 5 rational numbers between 3 by 5 and 4 by 5. Here I'm finding denominator to be same. Denominator to be same, although these two are rational number. In previous case I did between whole numbers, now I'm doing between rational numbers, but they are all like fractions. Why they are like fractions? Because they have same denominators. So, the fractions having same denominator called like fractions. So if there are already like fractions between 3 by 5 and 4 by 5, I do not find any numbers to be visible. But this can be done very easily. You can write 30 by 50, multiplying by 10 again, because limited numbers are there, only 5 rational numbers. So 30 by 10, 10 multiply this by 10, multiply this by 10, multiply this also by 10. So do whatever you are doing to the first number, do the same to the second number, and you convert it into equivalent fractions. So these are conversion of them into equivalent fractions. So 30 by 50 and 40 by 50, and there are little bit of a space now created. So you can say 31 by 50 is the first number, 32 by 50 is the second number, 33 by 50 is the third number, and this goes up to 39 by 50. So again you are coming with 9 numbers. You have to find only 5. So you can take either of these 1, 2, 3, 4 and 5. Here you can stop because you have to find only 5. Even you can have lot of numbers in between this, that is 9 numbers are still there. So out of that you have selected 5 and left all those. You can take either of the numbers between 31, 33, even 35, 38, 37, like that. There is no need to take it in order, but they are all lying between 30, 3 by 5 and 4 by 5. So in this case I found the numerator to be different and denominator to be same. So those were like fractions. I simply multiplied both of them by 10 and 10, and I did not do a lot of work here. But if the denominators are different, then what to do? So this is denominators are same, they are like fractions. If they are unlike fractions, unlike fractions having different denominators. Suppose this is 3 by 4 and then say 3 by 7. So these are unlike fractions because they have different denominators. So they are unlike fractions. So how to change it into like fractions? First step should be to change it into like fraction, and to bring it like this. So take the LCM of 7 and 4. The LCM of 7 and 4 is 28. So make it 28 first. So 4 7 are 28. Multiply it by 7 and divide by 7. So this is 3 into 7 by 4 into 7. And this is 7 4s are 28. So multiply it by 4 and multiply it by 4. So you have changed it into like fraction. That is 21 by 28 and 12 by 28. And now you are getting a little bit of a space between 12 and 21. You can write the numbers are, I'm starting from here, 13 by 28, 14 by 28, 15 by 28, 16 by 28. And if they are asking you only 5 numbers, then this is finishing here. 16 and 17 by 28 are the numbers between 3 by 4 and are the rational numbers between 3 by 4 and 3 by 7. So you might have been clear now. If they are like fractions, means having same denominator, not leaving any doubt here, then simply multiply by 10, divide by 10. Here also multiply by 10 as you are doing in previous sum. So this is 30 by 50, 40 by 50, and find numbers between these two: 31 by 50, 32 by 50, 33 by 50, 34 by 50, and these are the numbers between 3 by 5 and are the rational numbers between 3 by 5 and 4 by 5, because those were like fractions, so could be done easily. But here in case of unlike fraction, what do? You convert them into like fraction by taking the LCM and finding the LCM, then changing it into like fraction. Both are changed into 28. As they are changed into 28, the upper numerator also changes. Multiplying and dividing by 7, here multiplying and divide by 4. So this is 7 3 are 21 by 28 is equivalent to this. This is equivalent to this, and this is again equivalent to this. So equivalent fractions are there, but simply changing the things into like one. And once it is in like fractions, then this is giving you a lot of space between 12 and 21. You are getting 13 by 28, 14 by 28, as I have written here. These are the numbers between these two. Still you can have to calculate 50 numbers. Then what do? Simply multiply it by 10, multiply it by 10, multiply it by 10, multiply it by 10. You can get a lot of numbers. There is no dearth of numbers at all. In between two given numbers, you can find very easily rational numbers. And you can find this in case of integers, negative integers also. For example, someone says find, I'm taking the examples myself, not in the book, not from the book. I'm not taking anything from the book. I'm doing it just by myself. This is minus 3 by 4 and 1 by 6. And they ask you find 5 rational numbers. This time I have taken one negative and one positive rational numbers. 5 rational numbers between these two. So for the sake of practice, I'm taking a lot of sums by myself, not taking from the book, but giving you good concept of that. That again, I'm finding these to be unlike. So these are unlike fractions. What is the first step? These are unlike fractions because denominators are different. So what do? Make the denominators equal. So how can you make the denominators equal? Take the LCM of 4 and 6. And LCM of 4 and 6 is done by this way: 2 2 are 4, 2 3 are 6. Here 2, 1 and 3 and again 3 1 unless and until 1 1 1. So 3 2 is 6, 6 2 is 12 with LCM. 12 is the LCM. Convert each of them into 12. So minus 3 by 4 into 3. So whatever you are doing in the denominator, you have to do the thing into numerator also. The other is 1 by 6 multiplied by 2 multiplied by 2. These are changing into like fraction now. So this is 3 3 is minus 9 upon 12 and 2 upon 12. And now you look for how many numbers you are getting between minus 9 and 2 on the number line. So if you look for that numbers minus 9 and 2, see the number line here. See the number line here. If this is minus 9, you're going towards right, the value is increasing, minus 8, this value is increasing, minus 7, value is increasing again, minus 6, minus 5, minus 4, minus 3, minus 1, 0, value is increasing. If you are going to right, the value is always increasing, 0, 1, 2, and stopping here because this is 2 by 12. So this is the boundary. Between these two boundaries, all are having 12, 12, 12 in the denominator. So how many numbers you can write? You can start from minus 8 by 12, minus 7 by 12, minus 6 by 12, and so on, be a 0 and 1 by 12, where it finishes, because you can take only up to this 1 upon 12. So these are the numbers between this minus 9 and 2 by 12. Lot of numbers are there, and they are asking you only 5, so you can take either of the 5 from here, 1 2 3, and even 5 by 12, and even 0, even 1 by 12. So numbers can be taken in between, but you should not exceed this, and you should not go beyond that, and you should not go beyond that. You take only the numbers this between this. So this is the way you can find rational numbers between two given integers, between two given whole numbers, between two given fractions, whether it is like or unlike. If it is unlike, you have to change it into like fraction, as I have done here only. And if you have any concept, you can write the comments, can ask your problem, and I can discuss it in the later class. Then there are some true and false questions also in question 4. They say state whether following statements are true or false and giving reasons for that. Every natural number is a whole number. Can you say that? Every natural number is a whole number. Every natural number is a whole number. So you should have the concept of natural number. As I told you, the set starting from 1 going up to infinity. This counting number which naturally came to the human being. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is natural counting numbers. This is the counting number starting from 1 only. And then came this discovery of 0 came, that is whole numbers by Indians. So whole number is 0, 1, 2, 3, and again it is going up to infinity. What is the difference you are finding? That 0 is present here, 0 is absent here. So can you say that every natural number is a whole number? Every natural number is a whole number? Yes, every natural number is a whole number because this whole set is present here. So every natural number is a whole number. But every whole number is not a natural number because 0 is differentiating between these two. So every whole number is not a natural number. What I'm saying you, every natural number is a whole number because I'm finding the whole set of natural number present here, and going up to infinity, this is also going up to infinity. So every natural number is associated into this bracket. But the whole number, if you want to associate it, 1 0 becomes extra. So if that is becoming extra, then whole number, every whole number cannot be a natural number. Then comes the second reasoning question. Second reasoning is true and false. Every integer is a whole number. Can you say every integer is a whole number? You can yourself judge. Integers are negative also, but whole numbers are always starting from 0, all positive. So every integer is a whole number. For that you must know the set of integers. The whole number you know well, whole number starting from 0, 1, 2, 3, 4, 5 up to infinity. But if I write the set of integers, I said you in the previous lecture that this never ends, it's negative infinity. Then suppose negative 5 dot dot dot, because in between there are so many large numbers, minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3 up to infinity, positive infinity. So you're finding this thing is only the part of this. So whole number are never negative. But here negative numbers also. So every integer cannot be a whole number because whole number can never be a negative number. That is always positive number starting from 0. So this is again false statement which is given here. So every integer cannot be a whole number. And every whole number is integer because that is true. Opposite is true. And then they say every rational number is a whole number. Every rational number is a whole number. You know, whole number starting from 0, 1, 2, 3 cannot be fractions. A rational number are of the form p by q, and those are fractions. They are bound to be fractions. It can be 2 by 3, it can be 1 by 4, it can be 0 by 3, 0 by 3 is 0 only. It can be 5 by 8, it can be negative 2 by 3, it can be negative 1 by 8, like that. So you're finding the things to be fractional. So every rational number is not a whole number because rational numbers are fractional. Whole numbers are never fractional. So rational numbers cannot be whole numbers, but whole numbers are also rational numbers. Opposite is true, but this statement is false. But a whole number, every whole number is a rational number. That is true. Every whole number is a rational number. Because if you write 0, 0 by 1, if I write 1, 1 by 1, if I write 2, 2 by 1, if I write 3, 3 by 1, I can write 1 in the denominator because they don't make any difference. So every time I am finding that these are in the form of p by q, where p and q both belongs to integer and q is not equal to 0. So this is a rational number, but they are whole number also. So whole numbers can be rational, but all rational numbers or every rational numbers cannot be a whole number because you're finding that fractions are creeping into this and fractions are not associated in this whole number set, and therefore this is gone with the wind. Gone with the wind. This is the exercise first which I was discussing for class 9th. But my main concern is the number which are non-terminating, non-repeating decimals. That is irrational numbers. This is the main concern for class 9th. Irrational numbers. Irrational numbers. Irrational numbers, as I told you, those numbers whose decimal representation is non-terminating, neither it will terminate, and non-repeating decimal. Neither it will terminate nor it will repeat. Non-repeating decimals. I'm showing you some numbers. If it terminates, then it is not irrational. If it repeats, it's not irrational. So it should not terminate, neither it should repeat. Those are irrational numbers. So as I gave you the example of pi only, if pi is written in simply pi, mathematicians have come with lot of calculations with larger number of digits, the value of pi, that is 3.14, and going up to infinity. So that never ends. So this is never terminates, never ends. That is not terminating, non-repeating. So pi is a rational number, is an irrational number, not rational, I'm sorry, because it is non-terminating, non-repeating. The value of pi is non-terminating, non-repeating. Then if I write 1 by 4, is it terminating or non-terminating? If I write 1 by 8, if I write 2 by 7, if I write 3 by 4, if I write 3 by 2, just check it whether it is terminating or non-terminating, and also check whether it is repeating or non-repeating. If I write 1 by 4, what does it mean? 1 divided by 4. Usually people commit mistake. They find the larger number and then divide 4 by 1. This is 1 divided by into 4 parts. So 1 by 4 means 1 divided by 4. 1 by 8 means 1 divided by 8. But what happens? The child is writing simply 8 by 1. Divide 8 by 1 and they come with the answer 8. But that's not true. What you have to do? Numerator is always to be divided by denominator, not the opposite. If you do opposite, you are doing blunders. 1 upon 4. 1 upon 4 means 1 divided by 4. I'm just checking how it goes on. 1, I'm dividing it by 4. So the people say 1 में 4 से divide नहीं होगा, but होगा. कैसे होगा? I'll put a 0 here because 1 is smaller than 4, so it doesn't go, so I'm putting 0 here. And then I'm changing this thing into point and putting a 0 here. So you're getting 4 2 ja 8. And 2 is the remainder. And if you again put a 0 here, 4 5 ja 20. So the answer is 0 remainder. So if remainder is 0, this is called, on division, if remainder is 0, this is called terminating decimal. So clear with terminating? What is terminating? If you divide numerator to denominator and express it in decimal, and you are finding somewhere that remainder is coming 0 in division process, so terminating decimal. It is terminating decimal. So 1 upon 4 is exactly 0.25. 1/4 is 0.25. And if I go for 1 by 8, if I go for 1 by 8, 8, again 1 is smaller than 8, so 0 here, put a point here, put a 0 here, 8 1 ja 8, 2 is the remainder, 8 2 ja 16, 4 is the remainder, 8 5 ja 40, and things are again reducing to remainder 0. So you're finding remainder 0 here. So on division, you are finding 1 by 8 to be a terminating decimal, and the answer is 0.125. So this is terminating decimal. This is also terminating decimal. What does it mean? That remainder must be 0. If I go to 2 by 7, what do I observe? Divide 2 by 7 here. Divide 2 by 7 here. 2 is again smaller than 7, so it will not go. Put a 0 here. Adjust decimal, adjust 0 here. 7 3 ja 21, more than 20. So 7 2 ja 14. Take remainder here 6. Put a 0 and keep on continuing the process. 7 8 ja 56. 4, your table must be strong. 7 5 ja 35 because division is tougher than multiplication. 5 7 7 ja 49. This is a continuous process, and sometimes people get frustrated, but you must carry on the process to check how this is taking the shape. 49 1, put a 0 here again. 7 1 ja 7, 3, put a 0 here again. 7 4 ja 28, and here you are getting 2 again. So the same cycle is going to repeat. You just see same cycle is going to repeat here, because if I put a 0 here, then again this process is repeating. So 2 8 5 7 1 4 2 8 5 7 1 4, and so on. So what are you finding here? It is not terminating. It is a non-terminating. Why? Remainder is not coming to be 0. On on further division, after how many steps you are getting 0? Nowhere. You're not going to get 0 here. So this is called, where remainder is not coming 0 is called non-terminating decimal. And also I am finding that this whole period is repeating. 285714, 285714, 285714. This is just a ringing process, ringing in your brain. So the answer becomes 0.2855714. Since it is repeating, so we don't write it several times, you put a bar over this. This bar indicates that the whole set is repeating. So you found that your remainder is not equal to 0. Therefore, this is a non-terminating decimal. But it is repeating. So this is non-terminating repeating decimal. So rational numbers can be of two types. These all are rational number. These all are rational number. These all are rational number because they are all written in the form of p by q, where q is not equal to 0. On division, I find that some are giving me remainder 0, so they are terminating, and some of them are giving me a ringing thing. That is called non-terminating because remainder is not coming to be 0. I keep on dividing, that will keep on continuing, and never I will get tired, but it will not give me any answer. That will keep on repeating. Just the period is repeating or a one digit is repeating. Sometimes one digit is repeating. Sometimes you will find that the whole set of numbers is repeating. So this is non-terminating and repeating decimal. So rational numbers are of this type, that can be either terminating or non-terminating and repeating. But what about this? This is neither terminating nor repeating. So this is not repeating at all. Even it will not repeat. This whole set of period is repeating here, that you will not find here. What are that set of numbers? I have to find that. 3 by 2, this will give you clearly 1.5. And if you divide 3 by 2, just check it. This time 2 is smaller than 3, so I'll give 1 jar. 2 1 jar 2, 1 is the remainder. If I point here, if I put point here, if I put 0 here, 2 5 jar 10, and things are disappearing. So remainder is 0, so terminating and no repeating. So this is terminating decimal. So these are all set of rational numbers. Why I am doing this in this chapter of irrational numbers? I am talking of rational because I have to make a comparison between these two, and you must have a clear-cut concept of rational and irrational so that your answers must be very clear that if it is rational or not, or if this is irrational or not. So the rational and irrational are to be compared here. So rational numbers are sometimes terminating, sometimes non-terminating and repeating. But this is always non-terminating and always non-repeating. Rational numbers. These are the examples of rational numbers, and I have shown you all the division process of finding whether it is repeating or non-repeating. But my concern was irrational number. So one example I already gave you, that is pi. Pi is a non-repeating, non-terminating decimal. Mathematicians have come with several digits after decimal and they do not find it repeating, neither they find it terminating. So what are other numbers which are non-terminating? You might have seen that if I write root 2 and find the square root of 2 by calculator, this is again coming to be non-terminating, non-repeating. Nowhere you will find remainder to be 0 if you find the square root of 2, and also nowhere repetition is taking place. Root 2 is approximately 1.414 as I remember, and this can go on, no termination, no repeating. Root 3 again 1.732 dot dot, but non-terminating, non-repeating. Neither the remainder will be 0 on finding the square root, and nor this will ever repeat. If I write root 4, what about this? This root 4 comes out of a square root and that gives you 2. And 2 is 2 by 1. So this goes into the series of rational number. Now you might have observed that why I'm writing these two things together, rational and irrational together, because I have to make a comparison between these two. So those numbers which come out of the square root, those are perfect square numbers. What are perfect square number? 1 is also a perfect square number because 1 come out of the root and that gives 1 only. 1 square root of 1 is 1. So this is also a rational number because 1 by 1 is a rational number. So 4, 2 by 1, rational number, 4 is coming out. But what about 5? If you write 5, it never comes out of root. And also it never gives you terminating thing, neither repeating thing. So root 5 is again irrational numbers. So root 2, root 3, root 5, even root 6 not coming out of this square root. Root 7, root 8 even, root 9 is not a rational number because this gives 3 and 3 is rational. So it is not an irrational number. And root 10 is again irrational. Root 11 is irrational. So you might have observed that the things which are not coming out of the square root, those are irrational numbers. So every time I am finding that root 2, root 3, root 5, root 7, root 11, root 6, root 8 are irrational numbers, because if you find the square root of these numbers by calculator or by any other means by own brain, you will find that the never it is that the remainder becomes 0 on further calculating a square root, and nor it is repeating at all. So non-repeating, non-terminating decimals are the set of the examples given here: root 2, root 3, root 4, root 5, root 7. These are irrational numbers which are other than pi, which are also irrational. Now I'm telling you a little bit of definition that how to plot this irrational number on the number line. You can plot even rational number on the number line. That is beyond the course because that was taught in class 8 only. Here you have to find how to represent root 2 on the number line. A representation of root 2 on the number line. A representation of an irrational number. First irrational number is root 2. Root 2 on the number line. So for this I use a little bit of geometry and use a Pythagoras theorem. What Pythagoras says, Pythagoras theorem is to be used here. It says perpendicular square plus base square equal to hypotenuse square in any right triangle. This is made use in this process. And you know, Pythagoras was a Greek mathematician, and he was famous mathematician of and also a philosopher. He was the first to discover irrational numbers in 400 BC. These numbers are said to be irrational numbers because they cannot be written in the form of P upon Q. So as I told you, those numbers which are not rational are called irrational numbers. Or there are many myths about his, discovery. But here we don't go for myths. We just want to plot it, how to write irrational number on the number line. So what do you do? What do you do? What do you do? Root 2. So plotting root 2 is easy. You take a number line here, put 0 here, 1 here, and so if you want to plot root 2, you have to pick perpendicular as 1 and base as 1. So if you write 1 square plus 1 square, it becomes hypotenuse square, and then 1 plus 1 is h square. So h square is equal to 2, h becomes root 2. So what you have to do, you have to take a scale where perpendicular is taken one unit and base is also taken as 1 unit. So what I'm going to take that here 0 to 1, I am taking O to M here. This is the base for the Pythagorean theorem. And here I'll draw a perpendicular with the help of protector, or you can use compass here and draw a straight line here, 90-degree angle, because I have to make a Pythagoras theorem true. So I'll take Pythagoras concept. So this is 90-degree angle, and here the base and perpendicular I have taken the same. So this is 1 and this is also 1. So MP is also 1. OM is 1 unit. and MP is also 1 unit. And now if you take your compass here and join it with the help of scale, this becomes hypotenuse, and this is representing root 2. Why? Because OM square in triangle OMP, this is a right triangle clearly, OM square plus MP square is OP square, as I have written here 1 square plus 1 square is OP square. So OP square is 2. So OP becomes hypotenuse, that is root of 2. Square root of 2 is represented by OP. So now take O as the center and OP as the radius. Taking O as the center, now taking O as the center and OP as the radius, I'm mistaken, this is R, radius, this is to be deleted, this is to be deleted here, this is to be deleted, OP as the radius, we draw an arc. We draw an arc like this, O at the center, P at the radius, OP at the radius, we draw an arc like this, which intersects the number line at some point, which intersects the number line at some point, which intersects the number line at K. An arc which intersects the number line at K. So K is the point on the number line, therefore K is the point on the number line which represents root 2. So this is root 2 and exactly this is going to be 1.4. So this is going to be 1.4. So this point K is the true representation of root 2 on the number line. So usually what we do, you have to make use of Pythagoras theorem, and if you have to represent some more numbers, you have to have some practice over this, and clearly in other classes I'll be discussing how to represent root 3. I'm not going to discuss root 4 because that is a rational numbers. So root 5. For doing root 5, what will be the base and what will be the perpendicular? If you want to draw root 5 on the number line, how will you do it? The best way is to split this 4 into two perfect square numbers. Express 5 as the sum of, and that cannot be easy always, sum of two perfect square numbers. But this time it is easy. What are those perfect square numbers? I can write 2 chi square. This is perfect square number. 4 is the perfect square number. So I'm writing 4 plus 1 and 1 chi square. Both when squared and added is giving you 4 plus 1, 5. So if this number is expressed as the sum of two perfect square, then the drawing is easy. But if this number is not expressed in the sum of two perfect squares, then the sum becomes difficult. You have to take the help of the other number. As I have skipped here root 3 because I know that that will be difficult. So I'll be discussing in the next class. With root 2 you can do root 3, but there is no other way that 3 can be expressed as the sum of two squares. 3 is not a number which will give you easily the way, but 5 is giving you the way. So if 5 is giving you the way, so how do you do this? So I'm showing you in the next page. I've taken 2 square plus 1 square. So I will take perpendicular as 1 and base as 2 this time. So if I draw this number line like this and trying to represent root 5 on the number line, trying to represent root 5 on the number line, I was lucky enough that I got two perfect square numbers. that is 2 square and 1 square, which gives me 5. So 5 can easily be expressed. So I'm writing 0 here as I have written in the previous case. I'm taking the base as 2 units here now. So this is 1 unit, this is 2 units. So this is the base. From here to here it is base. I am taking this as base. OM is the base. And at this point you draw again 90-degree angle with the help of compass or protractor, whichever like, but compass is better to be used. And here you will take perpendicular as 1 only because you've taken this as the base. So OM is 2 units and take this as 1 unit. PM as 1 unit. You can do either way. If you take this 1 unit, this should be 2 units. The triangle will be a little bit lengthier, but the sum will go on like that only. You can take either of the two. So I have taken OM as 2 units and PM as 1 unit. And again, I'm joining this thing with a scale. So I'm getting this as 5 units. So this is 2 square and this is 1. So 2 square OM square plus PM square equal to OP square again. So 2 square plus 1. This is to be written in the sum also because in case of this is total geometry presentation. So you have to write this. So this is 5 root will give you OP. So OP represents root 5 on the number line. But that is to be drawn on the number line. So taking O as the center, OP as the radius, draw an arc which will intersect this on the number line here. So this is the exact K which will represent root 5 on the number line. And this is 2.23 I think. So this will be your representation of root 5. I have skipped root 3 here because root 3 cannot be done so easily because 3 cannot be expressed as the sum of squares of two numbers, two perfect square numbers. So I'm skipping it for the next time. But my purpose is to tell you everything of representation because this representation is asked in the paper. So this is to be done very clearly. You can easily practice root 8 on the number line. That can be easily done because this can be expressed as 2 square plus 2 square, two perfect square numbers. This is 8. You have not to draw 9 because 9 is a rational number. So 10 can be expressed again. I am giving you the hint only. So you can practice it at home. 3 square plus 1 square. So you can take base as 3 and perpendicular as 1 and draw this thing and do the same process. For 10 it can be 3 square plus 1 square. For 8 it is 2 square plus 2 square, 2 perpendicular, 2 base. 11 is again tough. 11 is again tough. And 13 is easy. 13 is easy. 12 is again tough. So 13 is easy. 13 is 3 square plus 2 square. 3 perpendicular, 3 units and base 2 units. So 13 is easy. So this 8 you can represent root 2, root 5, root 8, root 10, root 13 easily. You can do these things very easily. But for others, for example, if you want to do root 3, root 6, root 11, for these you have to take the help of the previous number. So for root 2 you have to take the help of for root 3 you have to take the help of root 2. First you draw root 2 and then you do root 3. Otherwise you cannot do. Again here for 6 you do 5 first and then with the help of 5 you can go to 6. For this 11 you do 10 first and then with the help of this 10 you can go to 11. So that I'll let you know in the next session because this session will continue. This is the beginning of the class and I have started taking it just now. So it will keep on continuing for the next session. Continuously the classes will be discussed. Every time the problems will be discussed. If you have any doubt you can ask me in the comment section of my YouTube channel. Find the decimal representation of 10 by 3, 7 by 8 and 1 by 7. These all you know that how to divide and keep on continue dividing, continue dividing. Sometimes you'll find the remainder to be 0, so that is terminating. If the remainder is not 0, that is non-terminating. So they are discussing case 1 where remainder is 0, that is called terminating rational number. and our remainder is not 0, but still it is rational. That is 10 by 3 or 1 by 7. It is repeating, so that is called non-terminating, non-repeating decimal. No, non-repeating and non-terminating and repeating decimal. I'm mistaken. Sorry for that. So this is all about representation of the number line. This is the geometrical aspect of mathematics which I am discussing here. But sometimes if you divide 1 by 3, this is again I'm coming on the rational number only, rational part only, 1 upon 3. You might have seen if you divide 1 by 3, it is a rational number because it is in the form of p by q, where p and q both are integers and q is not equal to 0. This is a rational number. But what type of rational? This is a rational number which is non-terminating but repeating, which is non-terminating but repeating. Just see 3, 1 is less than 3, so 0 here. Put a 0, put a point here. So 3 3s are 9. And this starts repeating from here only. 3 3s are 9. 3 3s are 9. So I'm finding the remainder is not equal to 0. Therefore it is non-terminating because remainder is not 0. And it is repeating. So repeating 0.33333. So what to write for this? 1 by 3 in decimal can be written as 0.3, and this is single digit, so this is like a bar here. So this bar represents that this number is repeating continuously. So 0.3 is the representation of 1 by 3 in decimal. This is clearly non-terminating but repeating. If it would have been root 3, then it is non-terminating, non-repeating. That is clearly another wing of number system. So what is my concern to discuss this thing? That sometimes you will be asked to convert this recurring into fraction. What will you ask? Conversion of a recurring thing. That if asking this conversion of this into fraction, into rational numbers. How will I go opposite? I was given 1 by 3. This is a rational number. I brought it into points, that is repeating decimal. But if this is given and they say you to change into this, how will you do it? Conversion of this into the form of p by q, rational number. So they will ask you the question 1, express in the form of p upon q. The first question is 325 upon 8. I'm mistaken here. This is 3.25. 3.25. No repetition, nothing. This is to be expressed in the form of p by q. That is simple decimal removal. This second is this is non-terminating. Repeat. This is terminating decimal because this finishes here. 0.3 bar. I'm taking the same question from the above. 3 is 0.37 bar on both the digits. 3 0. One of the digits is skipping, and on other two digits they are putting some bars. All are done in different way. You cannot do the sum by the same process every time. And these are the questions I'll discuss in the concurrent lecture. I'm just putting the questions here, and that I'll be taking in the next class. So fifth is, and you have to ponder over that. Okay, what is the concept? How can you change this into fractions? And the other is 0.223, and all those are having recurring decimals. Clearly, this is a terminating decimal. So this is 325 upon 100. because if you remove this point from here, so you'll count 1 2 digits, so 325 by 100. This is the first solution because there are 2 digits. So if I remove this point 1 and 2 zeros, and you have to always reduce into simplest form. Every rational number is to be reduced into simplest form in the lowest term. So that is cancelled. The divisibility of 5 says that numbers ending in 5 and 0 are divisible by 5. So this is 5 6 the 30, 2 is the remainder, 5 5 0 25. This is short division I'm practicing here, and I'll tell the kids to practice this. And 5 0 10. First know the divisibility test and do it. Again, the numbers are ending in 5 and 0. So I know that numbers are divisible by 5. Again, numbers ending in 5 and 0 are divisible by 5. So if you divide this number by 5 as you have done in previous case, divide by 5. What are you getting? You are getting 13. Your table must be strong. Again, I'm saying you for the mathematics study and mathematics teaching, your tables must be strong. And which I'm finding in Delhi, people are having very poor concept of table practice, and therefore they are lacking in sums. So 5 13 just 65 and 5 4 just 20. Here it is reduced in the lowest term. So this is the answer. If you divide 13 by 4, you will get again the same answer 3.25. So this is the same way going opposite like this and coming to this. This is in the form of P by Q, which is a rational number. One of the sum I have done. The next sum which I am keeping for practice is zero point 0.3. Better I should continue this, but I'll take up these 3, 1, 2, 3, 4 sums in the next session because the dose will be enough for today. So I don't want to take, I'm taking the photograph of this on mobile and keep it for the next class because I'll forget the things what I've taught you. So better to have a good grip over the subject which I'm teaching you. So I would like to have the photograph of this so that I can continue from this onwards. And if there is any doubt, you can ask me in your comment section that, sir, I do not know this thing in rational or irrational numbers. But chapters must be concerned, which I am continuing. The next chapter will be discussed next time, but this time you have to have questions from this topic only. Thank you. Nice to see you again for the next class. Thank you again.